glass evidence. By the time we're done with this lesson, you will be able to tell which of these two fractures happened first. First of all, glass is identified by different components, but specifically the two components that we look at are the density and the refractive index. Glass is also manufactured for cooking, windshields, lab use, jewelry, and so many other things. At a crime scene, we might find glass from a car accident through broken headlights, or maybe the windshield or passenger side windows are broken. At a break-in, we could find shards of window glass, maybe fibers from the perpetrator's sleeves, or blood if he cut himself on the glass would be present as well. Shots that are fired into a window, we can tell the sequence and direction of the bullets, and minute particles of glass may be transferred to a suspect's shoes or clothing and can be trace evidence. Remember that this refers back to Locard's principle of exchange, and in this case, glass can travel very far distances. If we look at the history of glass, glass can form naturally, just like in the movie Sweet Home Alabama. It is true that you can capture that energy from the lightning and turn sand into glass. From erupting volcanoes, we get things like obsidian, that beautiful black shiny igneous rock, which is used as a cutting tool and sometimes still used to make something as sharp as a scalpel. Glass blowing began during the 1st century BC, and we get those beautiful pieces of glass. And one of the earliest forms of glass was actually made accidentally during food preparation in Syria. And glass is actually an amorphous material, which is hard. An amorphous meaning that it has a random arrangement of atoms made by melting sand, lime, which is calcium oxide, and sodium oxide at very high temperatures. Once it's cooled, then we can cut it, polish it, and make it into the structure that we want to use. Because of the random arrangement of atoms, it fractures in different patterns. So that's one way that we can actually individualize glass. The primary material used to make glass is silica, or silicon dioxide, which is SiO2. We add sodium oxide to reduce the melting point of silica because it needs such high temperatures in order to melt, and sodium oxide helps bring that temperature down. And we add calcium oxide, or soda lime, to prevent the glass from actually being soluble in water. But soda lime glass is actually a type of glass which is very inexpensive and easy to melt and shape. Your normal everyday glassware would be soda lime glass. Leaded glass is going to be found in fine crystal used for holidays, which uses a lead oxide instead of a calcium oxide to reduce that melting point, and the lead makes the glass much denser. It also helps give the glass really shiny appearance. Pyrex or Kymax, we see Pyrex more often. It's used in oven or lab glass for those clear baking dishes or the beakers that you see in the lab. They can withstand really high temperature changes, and we can make the glass different colors if we add different metal oxides, such as nickel oxides will turn the glass yellow to purple, cobalt purple to blue, and selenium oxides turn it red. So if we look at the properties of glass a little closer, the first one we'll look at is density. And each type of glass does have a specific density, as we can see in this chart here. Bottle glass is about 2.5, and then if you look at the lead crystal, it's around 3, which is quite high. It's very dense compared to the other types of glass. To find density, we just use the formula D equals M over V. And to find mass, we're going to use a balance. And to find volume, when we do the lab, we'll use the displacement method, but not what you remember of just putting the piece of glass in the water. It's not big enough or takes up enough volume for the water to rise. So we'll actually take the volume by measuring the mass of the water that's displaced when you place glass into the water in a beaker. Looking at the other property, it's refractive index, which is the speed of light in a vacuum divided by the speed of light through that particular substance. So we know that light in a vacuum travels at a speed of 300,000 kilometers per second, which is unknown, and then we can solve for the other substance. And if we talk about refraction, it's the change in the direction of light as it speeds up or slows down when moving from one medium to another. So when we're talking about medium, we can talk about air to water, we can talk about different oils. In the lab, we'll use water, clove oil, and vegetable oil, and see the different behaviors of the light. If we look at this beaker of water, we can see that this piece of glass, you can see it, and it looks magnified. We actually say that the Becky lines are visible on the inner portion of this glass, which is the Becky lines are like a halo that form, and it sort of looks like it's magnified. It's bigger than it would be. when you can see the glass through the water, we know that there is a different refractive index, RI standing for refractive index. When the refractive index is greater than the liquid, it'll appear to have the Becky lines inside and it'll be magnified. If the refractive index were smaller than the liquid, it would be the reverse. If we look at this beaker, we can see that the glass appears to disappear. That would mean that the glass has the same refractive index as the liquid that it's immersed in. Looking at fracture patterns, we know that glass actually does have some flexibility. So when it's hit, it stretches slightly, and we say it reaches its kind of elastic. It has a certain point, but after it passes that elastic point, it does break. The first fractures are primary radial fractures, and they're formed on the opposite surface of the glass when it breaks. If we look at this slide, oops, go back there for you. We can see the different fracture patterns. And the secondary fracture is actually concentric fractures, which form on the same side as the impact. So we can see the concentric fractures right here. You see these little lines that are going in between. These are the radial fractures. Those are the primary, and remember we just said that they form on the opposite side of the glass, but they form first because the glass stretches and breaks on the opposite side. We may actually also see concentric cracks that are not perfectly circular like this. Being concentric means that it has the same center. So if we look at this, we can, where my pen is going now, we can see that we might see concentric cracks that are randomly placed like that. But those are also concentric cracks, and they happen on the same side as the impact, but they happen after the radial cracks. So the reason that these cracks form is that glass, when it's hit, it stretches a little bit. So on the side where the impact takes place, it's actually being compressed or squeezed together, and on the opposite side, it's under tension. And glass is much weaker under tension than compression. So it breaks first on the weaker side, which is opposite the strike, the side that's under tension, and produces those radial fractures. For bullet fractures, we know that the bullet is actually going to push some of the glass ahead of it, causing a cone-shaped piece of glass to exit along with the bullet. And the exit hole is larger than the entry hole because as it hits the glass, it's actually going to slow down a little bit. So if the bullet was fired perpendicular to the window pane, the entry hole of the bullet will be round. So if we look again in this section here, this is a round hole. If it were fired at an angle, we can help locate the position of the shooter that way because the hole will be elongated in one direction or another, if it were right to left or left to right. We can also sequence the order of the bullet holes because of the radial cracks, which will terminate in one another. So if we go back, we can see that this line here, we have this nice long radial fracture, and then we see that this fracture line, this radial line here, stops at this fracture. So that tells us that this crack happened first, that impact, and then this one happened second. Okay. If we look at the different types of glass, we can first start with bulletproof, as we're talking about bullets. And what it is actually a combination of two or more types of glass, one hard and one soft. And we say it's bulletproof, but it's really more like bullet resistant. The softer layer makes the glass more elastic, so it absorbs some of the impact when it gets to the harder glass. But the refractive index of the two has to be really close so that it can be transparent. You can see through it. And the range in thickness will range anywhere from 3/4 of an inch to 3 inches. Tempered glass is glass that's been treated with heat tempering or annealing to make it stronger. So it's brought up to really high temperatures and cooled and brought up to those temperatures again. We find it in the side windows of the car or the mirrors or the rear windshield also. And it's fractured into really small fragments instead of sharp shards. And we say it dices because it forms these like little pieces of dice. And it's a safety feature, so it's not as sharp. Laminated glass is actually two layers of glass that's bonded together by a layer of plastic in the middle. And we say that it cracks and it's not supposed to shatter, which is a safety feature, and that's why we use it in windshields. I have some other information about glass. Backscatter is kind of a phenomenon when glass shatters. Most of it goes forward with the impact, but some of it flies backwards, and those pieces of glass might be caught in fibers or parts of clothing, shoes, that can be traced back to the crime scene. During a fire, breakage patterns form, but they're in wavy lines, and not necessarily, you won't find those concentric and radial cracks, but we can find more of those cracks around regions of higher temperature, so it helps locate where the source was. We find other scratch patterns on glass, for instance, windshields. If you don't clean the windshield wipers or you let them wear down, you can scratch that glass, and that will help individualize a car. Say, if it was part of the crime scene, we know that we have some glass that has those cracks on it. And with the speed of an object, the faster the object is traveling, the less marks that are going to be present. So that bullet, as it moves, the entry hole is smaller than the exit hole because it's moving faster as it hits the glass. But once it hits the glass, it slows down, so it has more marks on the outside. Or if a rock hit the window, it's traveling at a slower velocity, you're going to have a very irregular breakage pattern. When we collect glass evidence, we're going to first identify and photograph the samples. We'll collect the largest samples first. We'll figure out which is the outside and inside surfaces of the glass by looking at the conchoidal lines. Alright, those radial and concentric fractures on the sides of the glass. If there's multiple window panes, we have to make a diagram to figure out which one went where. We have to find other trace evidence such as skin, hair, blood, or fibers, make note of it, and package all materials, so those little pieces of glass will go into plastic vials, and the larger pieces will be put into secure padded boxes so that there's no further damage to them. And then after the collection, all the glass gets separated by size, color, texture, right? And then they're all kept separate so that we can get their densities and refractive indices, and then the pieces are cleaned so that we can do those tests.